Yes, a very good morning to all of you. We have Professor Sahu with us, and he is going to continue his talk from yesterday on estimation of error and maximum likelihood. Now, I request Professor Sahu to kindly deliver his talk. We welcome you, sir.
Okay, thank you. Good morning to all of you. Uh, yeah, can you see my full screen with
Yes, sir.
audio clear?
Yes, sir.
Yes, sir.
Perfect.
Yes, of course.
Yeah, thank you. Yesterday I left here and I thought of not discussing this particular example and migrating to more on error propagation, but for a completeness, let me brush up quickly. So, for example, you have a finite sample of measurement. So, I have measured length of an object. So, if you see, if somebody asks you what is the best estimate of the length of this object, as you can see, so this is a kind of measurement which we usually do in tabletop experiments in our teaching laboratories. So, since the errors in the measurements are instrumental, the measurements are Gaussian distributed, and I can find out the sample average like this. Okay, and my calculator will give me when I add a number like this. Okay, so what is shown in my screen on my screen. So then again using the formula for sigma square, and keep in mind since it is a finite sample and we agreed last time, my general formula should have n minus 1 in the denominator, not n. So then I calculate the arithmetic spread or standard deviation here, and I get this number. And how to quote this number at the end? So if you see, I told you that the final number should be mu plus minus sigma divided by square root of n. So that is the error on mean. So if you calculate that error on mean, so you are getting 0.0015. Okay, and the best estimate of the length which has to be quoted. You see, till now you are showing all the results as you are getting, and when the best estimate has to be shown or the final result has to be shown, so you have to round it off. So depending upon the precision, if I round it up, because you see now rounding up, if I make it after 3 digits, so it is 0.5, and 0.5 is equivalent to equal to 0.5, and then the rounding of rule says if the last significant digit is odd, so this has to be incremented by 1. So that is what I did to write 0.002, and since I truncated here up to 3 digits, so x average is also truncated to 3 digits, and there for the truncation, so if I am putting a point before 33, so 0.33 is less than 0.5, so I don't have to do anything. So that is the reason I wrote x is equal to 17.615 plus minus 0.002. So this example particularly I am showing to all of you because most of you must be handling the lab experiments in the teaching laboratories, and I urge you that you have to look into the calculation of mean sigma and the final estimation which is expressed as mu plus minus sigma by root over n. Okay, and proper rounding up has to be done. So this is just one example to make all of us aware, so in which way we should handle the calculations in the teaching laboratories. Okay, because I believe we are a mixed audience. Okay, so the uncertainty on the mean is given by the standard error of the mean and not the standard deviation. You have to keep in mind because statistics has to be taken into account. So this is sigma over square root of n. Okay, so this is just a caution or note. So now let's migrate to a different ball game, which is square root rule for counting experiments. So we know in laboratories we have done lots of counting experiments like nuclear decays, GM counter and all that. And in different other branches of science, you might have done counting experiments. So what is the rule? How do we code the errors properly in scientific literature? So the uncertainty in any counted number of random events as an estimate of the true average is the square root of the counted number. So that is the rule. And why it is square root of the counted number, I will convince you. So the average number of events in a given time, if you are counting for t interval, the t can be 10 seconds, 20 minutes and all that. So you have to write at the end the number nu plus minus root over nu. So nu is the number you have got by counting for a time interval t. So this counting experiment, for example, the examples could be number of babies born in a 2 weeks period in any hospital, radioactive decays at a random time period. Okay, so these could be counting experiments because a certain number is expected in that time interval. If you go to any hospital in any locality, they may be having a statistics. Okay, on the average, they expect these many number of babies to be born because you see that is controlled by the population, local population essentially. Some fluctuation may be there with respect to visitors and all that, but that is tiny. Okay. So you should remember that there is an expected average number. Okay, when you expect some average number, that follows a Poissonian distribution. Okay, and keep in mind to pronounce it as poison. It's not poison. Okay, so because many people, because of the pronunciation, they make it like Poisson distribution. It's not Poisson. It's Poisson distribution. So the birth has a average rate. Decays in large sample occur at a definite average rate. So all nuclear physicists, we know that the average rate is expected for the time period, and arrival of cosmic ray particles. So we expect certain number. So when we expect certain number or the average is expected, so that defines a Poissonian distribution. So then let me remind you about little bit about Poissonian distribution, although I assume that you have been taught or discussed in the past 2 lectures. So the probability of new counts in any interval, in any definite interval, is P mu nu. Okay. So where Poissonian distribution P mu nu is given by this formula, we know e to the power minus mu, then mu to the power nu and factorial nu. So this is the formula for Poissonian distribution, and I told you that Poissonian distribution will be applied when we expect certain number of average in a given interval of time. That is the trick to apply Poissonian distribution. So nu greater than 0 is expected mean number of counts in the concerned time interval. So now I will give you a homework, because you see I do the job and you do the job, so that will be a little two-way process. So the homework is, you find the first moment of the Poissonian distribution, and we know the first moment is the mean, that mu is the expected mean number of counts. That is, if I take average of nu, that should be equal to mu. Okay, so first moment calculation, you know it from quantum mechanics or any kind of distribution function. So further, you also should show that how to calculate the second moment, which is the standard deviation. So that sigma nu should be equal to square root of mu. Okay, so then this will go in our first formula within that bracket, which I have written the average number of events in time t. Okay, so being said about the counting experiments and the Poissonian statistics which has to be applied, and the final best estimate how it has to be quoted, now it is time to take an example. So because through examples we can understand much better. So in this example, consider the following series of measurements of the counts per minute from a detector viewing the radioactive sodium source. Okay, so we have 5 different measurements. The question is, what is the decay rate and its uncertainty? Okay, so now already the measurements are given for counts per minute. Okay, so since radioactive decay, as I told you, certain amount of measurement or decays are expected to the Poissonian distribution, and your mu cap or x bar will be equal to the average of these 5 measurements, so that is 2205.6. And when you go for calculating the error on the mean, so you will calculate this is average divided by n to the power root over, and you will find that this is your 21. And I remind you the formula for error on the mean. So then the total count rate can be written as 2206 plus minus 21 counts. Okay, and you have to round it up in a way, because below one count you cannot measure. Okay, so if it is coming in decimals, so you have to round it up to make it a whole number. Okay, and as you can understand, so somebody has taken each minute measurement, so making it 5 different slots. So if somebody else is going at a stretch for 5 minutes, will it make a difference? So answer is no, but your calculations should be proper. For example, when you go on calculating with a single sample of 5 minutes, the averaging at the rate for 1 minute has to be done at the end. Okay, so because we put error on the counts, so that is why your sigma has to be calculated from the total number. You add up the total number, or let's say you are getting the same number in 5 minutes, so that is your 11,028, and you take the square root. Okay, and after you divide 5, so you will exactly get the same number. And you have seen that how rounding up is done for x bar, because your count number of count has to be the whole number. So point to remember is you put the error and make the final number and divide by 5 minutes to make it the count rate. So don't do it at the beginning, because error has to be assigned to the number of counts. Yeah. So sometimes we may know in advance the rate R at which the events we are counting should occur. Sometimes it is known. In that case, the expected average number of events in a time t will be mu, because the number of events is actually rate multiplied by time, because the rate is your number of counts divided by time. So for a particular interval of time, the rate by multiplied by time will give you RT. Conversely, if the rate is unknown, sometimes rate can be unknown also, then by counting the number of events in a time t, we can get the estimate for mu, and hence we can recalculate R. So your R best could be mu best divided by t. Okay. So let me take one example to explain this. Say a student monitors the thorium sample of previous example for 30 minutes and observes 49 particles. Okay, and what is the answer for the rate of emission R in particles per minute? So since it is emitted for 30 minutes, the total number is 49. So it is 49 plus minus square root of 49. So that is the total number. When you calculate a rate, as I told you, rate has to be calculated after the error is assigned. So now rate is you look at the formula upstairs, what I have written, R best is equal to mu best by t. So this is 49 plus minus 7 divided by 30. So then, since a rate, since this is the rate, so rate can be written in fractions also. Okay, so this becomes 1.6 plus minus 0.2 particles per minute. So this is the way actually you have to proceed. So as you can see, I have taken examples from different books. The earlier was from Leo, and this is from Taylor. So yeah, and this example you can have a look at Taylor, I guess. Yeah, and let me omit this one. This is more involved, but anyway, that involves the statistics, Poissonian statistics. So let me go quickly to subtracting background, because sometimes you are making one experiment, nuclear experiment with a radioactive source in your laboratory, with, for example, gamma ray, beta ray, or alpha rays, depending upon the source. It might happen that you will get background from the cosmic rays. So how to deal with that in the counting experiments? So the thumb rule is the following: how to get the background subtracted. The events produced by a source is subjected to unavoidable background, as I told you, could be from cosmic rays, could be from any other source. What is the rule? First you count the total number, new total. So new total will be source plus background. So this has to be done for a longer interval of time because you need to build up statistics. So this is T total and you calculate the rate R, which is equal to R total is new total by T total. So now to calculate the background, you remove the source and measure the number of background events. And background estimation, people usually do not go for longer interval of time. So your T background is not equivalent to T total, it is much less. So then you calculate similarly the background rate. And after this is done, you calculate the rate of events from the source as the difference, which is your source is equal to R source is equal to R total minus R background. So finally you have to put the uncertainties on the numbers, okay, and following the square root of rule. And if there is a requirement, so then you may have to propagate the errors because this formula is essentially A minus B kind of formula at the end. Okay, so this is the standard rule of taking care of backgrounds in counting experiments. So this has a good discussion in John Taylor's book. Okay, so let me see how it is done. So radioactive decays with background. So a student decides to monitor the activity of a radioactive source by placing it in the liquid scintillator detector. So in course of 10 minutes, detector registers 2540 total number of counts, and this is with background. To allow for the possibility of unwanted background counts, so what he does is, he or she, removes the source and notes time in 3 minutes. So you see the original measurement is for 10 minutes and the background estimation measurement is for 3 minutes, 10 and 3. So the detector registers, of course, less number of counts because it is background, so it's 95. So to find the activity of the source, she calculates two rates, R total and R background, and all are, since it is rate, you have to calculate, you should calculate per minute. And their difference, R source is equal to R total minus R background. So what is the answer on their uncertainties? So as you know, the counting rule is square root rule. So your new total, the final number you should quote as 2540 plus minus root over of that number. Then if there is a requirement of rounding off, you do the rounding off. So you have certain number 2540 plus minus 50. Similarly for background, it is 95. So you make it 95 plus minus 10 because 95 root over, if you round it up, so this will be, it is close to 100, so it will be 10. So now you have to calculate the rate, and for rate calculation one was done for 10 minutes. So you divide by 10 and background was done for 3 minutes, so you divide by 3, okay, and you could get R total and R background. So now you have to subtract to get the source rate, okay. So once you do the subtraction, the mean value subtraction is easy, 254 minus 32, and then you are writing 222. But for the error part, it is error cannot be simply subtracted, okay. So this has to follow the addition or subtraction rule of quadrature, or the error propagation formula has to be applied. And once you do that, even irrespective of addition or subtraction, your errors will be added up. So keeping that in mind, so if you do 5 square plus 3 square root over, so that will give around, after rounding up, at 6. Okay. So this is the way your calculations will be done. You just counter check if people are doing this kind of calculation in your laboratory or not. Okay. And I told you sometimes null experiment setting confidence limits when no counts are observed. Okay. So I think we should discuss that because there are many experiments where no results are expected and we have to give certain confidence limit. So how that is done? So let me quickly go over through this and then we'll come back to the master formula for error propagation. So many experiments in physics test for the validity of certain theoretical conservation laws by searching for the presence of specific reactions or decays forbidden by these laws. So I'll give you one example. In such measurements, an observation is made for a certain amount of time because you are not looking into that rare event for an infinite time period. You are conducting the experiment for a certain interval of time. Obviously, if one or more events are observed, the theoretical law is disproven because as you know, if I give one example against your theorem, the theorem is disproved, but the converse is not true. Okay, so keeping that in mind, however, if no events are observed, the converse cannot be said to be true because you have observed for a limited interval of time. Okay, so instead a limit on the lifetime of the reaction or decay is set. So for if you want to report your null experiment in scientific literature, what you should do is a limit on the lifetime of the reaction or the decay you can report. Okay, so null experiment you should not be discouraged. That is also measurement. So now we apply Poissonian statistics because it is a discrete process and mean value is expected. So again I should remind you about the Poissonian distribution. A single trial of success is very less. The probability P goes to 0 almost, but the number of trials is so large, which n is going to infinite, that is a reasonable rate, event rate. Okay, so that is actually the rationale of Poissonian distribution. Yeah, somebody is speaking something. Is there a question? Yeah, if there is no question, so better not to disturb everyone, so you can mute yourself. So with this, so I can write the Poissonian distribution formula. So PR is equal to mu to the power R e to the power minus mu by factorial R. So earlier I used nu because this mixing of notations is because of different books. So let us assume therefore that the process has some mean reaction rate lambda. Then the probability for observing no counts in a period of time t will be calculated in the following way. So I should note here that the mean in the above equation refers to the mean number in the units of t, time, right? So if you can see e to the power minus mu, so mu should be dimensionless. So now if your unit is t, so then you have to put some constant which is the inverse unit or dimension of time. So now my mu I should write as lambda t. So that lambda is the inverse dimension of t because I told you that exponents of exponential and your arguments of the exponential and logarithmic, they should be dimensionless. So the above equation can be rewritten for radioactive decays and particle reactions as the following. I have just replaced mu by lambda t. Okay. So after this, when the probability of observing no counts I am looking for in a time interval t, so my R will be 0. So once I put R is equal to 0 in this formula, I will get P0 lambda is equal to exponential minus lambda t, taking R is equal to 0. Okay. So this is essentially the probability of observing no counts in a given time period t. So this is now can be interpreted as the probability distribution for lambda when no counts are observed in a given time period t. So that mathematical formula can be read like this. So we can now ask the question, what is the probability that lambda is less than lambda 0? So lambda less than lambda 0 is certain threshold. So this kind of calculation you have done already, and that is actually we know the probability of finding x between certain limit, okay, between lambda to lambda 0 kind of stuff. So that is calculated, for example, probability of x between x1 and x2, and this is given by the cumulative or the integral distribution. So you know about that. So this probability is calculated as the integral of px dx and calculated between the interval x1 to x2. So now if I ask the same question for our radioactive decay, what is the probability that this lambda is less than equal to certain lambda 0? So then I calculate the same equation with the limit 0 to lambda 0, and here a temp t is taken extra factor. This is to normalize the first expression, okay, because my calculation is done for the total interval of time t, I should normalize it. So to normalize it, I have put t by hand. So now my p0 lambda is e to the power of minus lambda t. So this probability is known as the confidence level CL for the interval between 0 to lambda 0. So the one I have written here, p lambda less than equal to lambda 0 is the confidence limit from 0 to lambda 0. So you may ask, is this confidence limit 0 to lambda 0 very unique? Answer is no. So now, before discussing that, so the confidence limit is defined as 1 minus of exponential minus lambda 0 t, and lambda 0 can be recalculated from this as minus 1 over t, natural logarithmic of 1 minus confidence limit. So to make a strong statement, we can choose a high confidence limit. For example, I should look into, for example, 90% confidence limit, and as I told you, for a given confidence limit, once I am putting 90%, the corresponding interval is in general not unique, because we are looking into that integral, the total number, and one can find other intervals which yield the same integral probability, right? So this x1 to x2 can be anything. So somebody may look for a bigger interval, for example 0 to infinite, and get the same integral value. So because of this reason, so the optimum solution is we should take the interval for which the number is high. Okay, the smaller interval is always better. That is the thumb rule. So for example, it might be possible to integrate this equation for some lower limit of lambda, which is lambda prime, for example, to infinity, and still obtain the same area under the curve. Okay, so I have taken 0 to lambda 0, but somebody can take from lambda prime to infinite and get the same number. So this will be only modified. Okay, so you should look into the certain smaller interval. So I remind you, the Higgs search, when it was done with null results, people essentially tried to localize the search in the mass spectrum, meaning let's find out the region where it is not expected, and then it is like, you do not know the mass, you are looking for the mass. So that is the reason you localize the mass by ruling out the mass regions where it is not expected. So it is similar kind of stuff. So the probability that the true lambda is greater than lambda prime is then less than 90%. So as a general rule, however, one should take those limits which cover the smallest range of lambda, because your search is not a wide search in the jungle, rather it is a confined search. Okay. So now let me take one example. So then this whatever I discussed, that will be clear. Otherwise, I feel it is not clear. Example is the best thing to make the things clear. So I am taking a 50 gram sample of selenium, radioactive. So, and I am observing for 100 days for a neutrino-less beta decay experiment. So neutrino-less beta decay experiments nowadays many people are doing, and so this reaction is forbidden by lepton number conservation. So if this is observed, this will be something like beyond standard model kind of decay, and many people are looking for it. So the current theory suggests that this might occur. So the apparatus has some detection efficiency. So let us say that the apparatus which is taken, that has 20% efficiency, meaning if 100 events are coming, it has the efficiency of registering only 20 events. So no events with the correct signature for this decay is observed. Can we set one upper limit on the lifetime of the decay and then establish that this is a rare event? So to do that, again I rewrite or recall the formula for the confidence limit, which was lambda 0 is equal to 1 over t log 1 minus CL confidence limit, and I have chosen 90% confidence limit here. So for lambda less than lambda 0, so I just use this formula, and when I recalculate, my lambda which is less than equal to lambda 0 is 0.115 day inverse, and here I have used 20% efficiency of the detector, which goes like 0.2, okay, in the denominator. So this limit must now be translated to lifetime per nucleus because I have taken 50 grams, okay. So then I have to calculate in 50 grams of this source what is the total nuclei. So this kind of calculations you know, and your n is equal to Avogadro's number divided by 82 into 50. 82 is the mass number of selenium. So now you have 3.67 multiplied by 10 to the power 23 number of nuclei. Okay. So then per nuclei, if you calculate, that is coming to be 3.13 into 10 to the power minus of 25 day inverse. Okay. And this lifetime is just the inverse of lambda, because I showed you earlier your lambda inverse is equal to your tau. So if you do that, your tau, since lambda was less than equal to this number, your tau will be greater than equal to 8.75 into 10 to the power 21 years, and I have to put my confidence level. Hello? Which was there is some noise. So if 90% confidence level, my tau is 8.75 into 10 to the power 21 years. So any lifetime which is 21 years, 10 to the power 21 years. So this is almost a rare process, and I could find out from my null experiment. So the neutrino-less beta decay may occur, but the time period I have taken, the sample I have taken with 90% confidence limit. So I put up a lifetime, and I found that if lifetime is so big, so it is certainly a rare process. Okay, so this is the way. If you have null experiments, you can set the confidence limit and report the lifetime in this way. Okay, so this example I would like to skip, and I would like to go to the propagation of errors, which is very important for me. Okay, so now let's quickly switch over to propagation of errors because we have lots of material in hand to discuss. So let's consider a quantity u, which is a function of two variables x and y, and x and y are the variables which I am measuring, and the corresponding errors are sigma x and sigma y. So I have to calculate the standard deviation or the error on u, this derived quantity u, and this has to be the function of sigma x and sigma y at the end. Okay, and the variance of u is defined in this way: expectation value of u minus u bar square. Okay, so now I can write my u, which was fxy. So this can be made a Taylor expansion around your mean values x bar and y bar. So this is written in this way, as you can see, and I rearrange it. So to calculate u minus u bar square, and if I do that, so with approximation, so you will find this can be written up to the second order like this. So now if I take expectation value of both the sides and then look into the both sides expectation values, so you will find my left hand side is nothing but sigma u square, and the right hand side is del f by del x square sigma x square plus del f by del y square sigma y square, plus I identify this is a covariance term. So I take 2 del f del x del f del y, and the term expectation value of x minus x bar y minus y bar is nothing but the covariance of x and y. So then the general formula in terms of correlation coefficient rho can now be written as sigma u square is whatever I have written within that square. Okay, so this becomes the master formula for any derived quantity which is a function of two variables. So meaning, so how your final function is related to the variable x and y, so that coefficient will come, then individual errors sigma x and sigma y will be there. If the measurements are not independent, there will be a correlation of the covariance term. So that is my third term. So this becomes the master formula for calculating error on a derived quantity u, which is a function of x and y. given the errors in X and Y. And I have not assumed these are independent. So the errors are quadratically with a modified term due to covariance. And we need to know the correlation of the quantities in order to estimate the errors on derived quantities, because the third term brings up the correlation. And when the measurements are independent, for example, there is no correlation, your rho can be set to 0, and then formula becomes easier, or the known formula. Usually we deal with independent measurements. When we measure length and we measure the width to calculate the area, so these two are independent measurements. So in those kind of cases, rho can be set to 0, and then my final formula is sigma u square is equal to del f by del x square sigma x square plus del f by del y square sigma y square. This can be generalized to multivariate analysis, right? So if you have many independent variables, so then this x, y can go up to any number. So that I can generalize that. So if you generalize, the master formula for error propagation for independent measurements becomes this. So you see, whenever you do any formula, any derived quantity, logarithmic, exponent, or any complicated formula you are going to deal with, which is a function of xi's, you don't have to remember anything. Just remember that a sum is there. Individual error square will be there because this is quadratic sum at the end, and this will be multiplied with how the function changes with respect to a tiny change in that variable xi. So your del f by del xi square sigma of xi, so that square. Then if you have multivariates, then corresponding terms will go on adding. So that will be your final formula for error propagation. You just need to remember this master formula for error propagation, keeping in mind that this is valid for independent measurements. So let me give you a couple of examples so that you digest that easily. So the error of the sum where u is equal to x plus y. So this formula will give you, again I am writing general formula for the sum, that is why the covariance term is there. So this is simply sigma x square plus sigma y square. And can you guess for what will be the error for the difference? Difference will be exactly same, only thing will matter in the covariance term. And if both are independent, so sigma u square is equal to sigma x square plus sigma y square. Okay, if covariance term is 0, there is no difference between the error on sum and difference. Both are same. And I exactly applied this formula of sigma x square plus sigma y square recently while calculating the R signal when background was there. So the relative error sigma u by u is much larger in case of difference because u is small. Okay, so once u is small, so same sigma u when compared to your addition, so this will give you a larger number. Relative error will be larger for difference. So similarly, one can calculate the error on the product. Okay, so apply the same formula which I wrote earlier, and you can, for the relative error, you can rearrange. For the ratio, again u is equal to x by y, so then you do the same thing, little bit of arithmetic or calculus, and you divide by u square, so you will get a similar term. So only thing is division and product. So what you will find is the covariance term is different, otherwise relative error is same. But again, once you calculate the relative error and put the percentage, so the number will matter. So like ratios may give you a difference compared to the product in the relative error. Okay. So now let me take one example. So this is a beautiful example. So in the classical method for measuring the polarization of a particle, such as a proton or neutron, is to scatter it from a suitable analyzing target and to measure the asymmetry in the scattered particle distribution. So if I am looking into polarization, so what I am doing is I am scattering into the whole phase space. Then what I do is, one can for example count the number of particles scattered to the left of the beam versus right, because it is asymmetry measurement, and the asymmetry is defined as R minus L divided by R plus L. For example, I want to see if the particles are emitted symmetrically in the whole phase space, or if I divide the phase space two hemispheres, left, right and left. So then there will be preferential emission. Okay, more particles are emitted to a certain direction. Then I can define this kind of ratio, and if there is any preferential emission, so this will be non-zero. And if both are same, R is equal to L, so then your asymmetry is equal to 0. So I can define this kind of ratios to study the asymmetry. So in this case, your sigma, your epsilon becomes a function of the counts R and L. And you use the master formula, take the partial derivatives, okay, and you calculate your sigma square epsilon, so which can be a complicated formula as you can see. And here wherever R plus L is coming, you can write also n total. So after doing those things and converting them to from the calculation of sigma R square is equal to R, because it is a counting experiment. So your sigma square epsilon can be written in the final form as 4 RL divided by n total Q. So now the question is, how do I know I am getting the right answer or no? So if you have a smaller asymmetry or no asymmetry, so you can actually set your R going to L, and if R is equivalent to L, so that can be equivalent to n total by 2. So if you plug in this in the formula you have obtained now, so your sigma epsilon goes like 1 over square root of n total, and that is expected, right? So this is the kind of formula we saw earlier. So this is the way to propagate the uncertainty of R and L and calculate the uncertainty on the derived quantity, which is the asymmetry parameter. Okay, so this is the way it is done, and depending upon your complicatedness of your formula you are dealing with, so you can similarly propagate. Only difference will come when you take the partial derivative. If your formula is a bit complicated, so your partial derivative calculation will be complicated, and once you have the final formula, you can calculate the error on any derived quantity. Okay. So the percentage of error, I can just quickly mention percentage of error. If you have two independent variables, f is equal to xy or x by y, we saw for independent variables there is no difference between product and division. So then this can be written in this way. So if you have x known to 3%, y known to 4%, then you know that xy or x by y or y by x could be known up to 5%. So that is the easiest example of quadrature, right? Because 3 square plus 4 square is equal to 5 square. Okay. And what you should note here is the percentage of error on a quantity and its reciprocal are the same, and the error on the logarithmic of x is just the fractional error. So these actually you don't have to remember. If you know the master formula, you can recalculate and answer all these things. And the thing to note is percentage errors add in quadrature rule. And for example, if I ask you, the mass is given and the volume is given, what is the best estimate of the density? And so then you go on calculating, so your density is mass per volume, and you propagate the error, or you use the formula which I showed you in the last slide, and that is essentially the error propagation formula I will give you, because this is a ratio. And then it is just a calculation. You plug in the numbers and you get your del m by sigma m by m, sigma v by v. You plug in all these numbers and finally you have your sigma rho, and then the rounding off has to be done anyway, and you know the rule. So this is the way to do it. It is very simple. So, and similarly, if you are looking for the Snell's law, so you can also do the similar calculation, because these examples I am showing because many people do in the laboratory, in the teaching laboratories. So similarly for Snell's law, you can do a similar calculation. So now, so since error propagation, I'm sorry. Since error propagation master formula is known to us, now let's move to error in matrix form. So will it give a better handle to us? So for general error calculation in teaching laboratories, you may not need matrix form. So what I am going to cover now, next 10 minutes or so, is essentially little advanced stuff. Okay, so that may be useful for nuclear physicist, high energy physicist, and whoever needs it. So now in the matrix form, let me take Vf as the error matrix of F, and Vx is the error matrix for X. X is my independent measurement and F is the derived quantity, that function. Okay, and then I can define my GKI as del Fk by del Xi, because you have seen these partial derivatives. Okay, so since you have seen this partial derivatives, so I have to bring in the partial derivatives somewhere. Yeah. So Vx and Vfs are symmetric and square matrices of size n cross n and m cross m respectively, and G has to be a rectangular matrix of m cross n order, because this has to be multiplied and this will be respected. You don't need to remember again these orders. So your Vf is equal to, in the matrix form, G Vx Gt inverse transpose. So for three independent uncorrelated variables x, y, z with errors sigma x, sigma y, and sigma z, so you can write your f is a function of x, y, z. Your g will be del f by del x and all that, because you know this kind of terms will come. You have seen in the error propagation formula. So now with all these things, error in matrix form could be written as V of x, then matrix multiplication of G, Vx and Gt transpose, and as you can see, I have taken Vx uncorrelated matrix because errors are independent. So your diagonal terms will stay sigma x square, sigma y square, sigma z square, and G transpose will be written, in this way. Okay, so if you multiply, you will get back the original answer, right? Because this we have seen earlier. The individual partial derivative square and your sigma x square, sigma I square. Okay, so this matrix multiplication is also giving you the same answer. But what is the beauty of matrix multiplication? So beauty of matrix multiplication is you can go for measurements which are not independent. You can go for infinite number of variables. Your matrix is bigger, and then in computation, in programming, you know how to handle it easily. Okay, so that is why matrix method is always good, and you don't need to remember many things. Let me take one example here. So I am taking three-dimensional geometry, and tracking chambers measure the position of particle in cylindrical polar coordinates r, phi, and z. R is known very precisely, meaning the error on R is 0. And phi and z are measured with uncorrelated errors. That means the correlated terms are 0. So you have sigma phi and sigma z. So now from this tracking chamber measurement of r, theta and phi, or r, phi and z polar coordinates, you want to come back to your Cartesian coordinates. This coordinate transformation is necessary sometimes. So somebody may ask, if your measurements are in the polar coordinates, can you come back to the Cartesian coordinates and show me what will be the errors on x, y and z? So you know this coordinate transformation, after the transformation things are mixed up, right? We have seen in the rotation problem. Okay, axis rotation problem, we have seen in the rotated frame, the coordinates will mix up. And this also we have seen in Lorentz transformation problem in special theory of relativity. So now let's go ahead, assuming that there will be mix up anyway. So we can write, we know the formula for x in terms of r and phi. So the x is equal to r cos phi, y is equal to r sin phi, and z is equal to 0, of course. So then I can construct the matrix G. So to calculate v, x, y, z, so I use the earlier formula of G, then your V error matrix, then G transpose, and I multiply everything. And after multiplication, so you see I have the error on x, y and z, and now you can see the first term is the if you write the formula for x, y, z errors, which will be independent, and you will find that sigma x square will be sigma phi square y square. That means it is mixed up, and your sigma y square will be sigma phi square x square. Essentially, I am looking into the diagonal terms, and sigma z square is sigma z square because this is not mixed up. Z is not affected. So this is the easiest way of calculating error in a matrix form. So now error ellipse and error matrix. As I told you, I am just going to little higher stuff so that people may need it. The advanced learners may need it. So for general use, so whatever I discussed, the master formula for error propagation, that is good enough. But for advanced learners, I am just exposing to little higher stuff. So the general equation for two correlated Gaussian distributions, okay, so we can write Pxy in this form where I have introduced this rho, the correlation coefficient. Now your Pxy is Px multiplied by Py because it's a joint probability, and to start with we take two independent distributions. However, one can choose another coordinate system where the errors will be correlated because of the coordinate transformation. As I told you, errors will be mixed up, correlated. Mixed up means correlated if I am going for a coordinate transformation. This I have seen from my classical transformation of the rotation, and also from Lorentz transformations. So I know it. So this represents a 2D error ellipse with correlation coefficient rho. So this is two-dimensional because I am just taking two parameters, two variables x and y. So now one can generalize to n variables also. So if it is n variables, the formula will be modified to a hyperellipsoid. This sounds very hard, but it is very simple in the matrix form. So now if I define the error matrix M as this, okay, so I am not saying it is independent because my correlation coefficient is there in the off diagonal terms. So I define this error matrix, and I define the discrepancy vector x minus x bar. So this discrepancy vector is essentially your sigma x, sigma y. Okay, and then I just recalculate my M inverse which I need it, and using my M determinant also. So after these calculations, so my Px Py will be modified to this formula, and that is essentially in a matrix kind of form. Okay, the formula which is written on the top is equivalent to the formula written at the bottom, but the way of writing is different. Now for n correlated Gaussian distribution variables, so I can generalize that because that is a simplified formula. So my matrix M will be very complicated because it's n dimensional now. I have defined n correlated n number of variables. It is very complicated, but computation wise this should be very easy. I don't have to care. I know in programming I can just take any dimension and go on doing it. So this could be written in terms of the chi-square for n variables. Okay, so simply the argument of exponent I can write chi-square. So this gives me very simplified formula, right? It's very simplified formula with chi-square as xt x transpose m inverse x. So now I know if I have transformed to another coordinate system, so my error matrix or error ellipse, the formula is much easier. Now, what is the general transformation of errors? What is the rule? So we suppose a set of variables xi, the error matrix is m, and we want to transform to another set of variables yi. So it is essentially a coordinate transformation, the way I did for polar coordinates to Cartesian coordinates. So now the Taylor expansion about the mean will be like this. Yi can be written as y average, and then this kind of terms if you have seen my derivation of the master formula for error. So now I can just rearrange to write like this. Okay, and from this second line I can write in terms of yj also. So I do that, and then with simplification with simplification I can get that final formula of my, and you can see again those terms which are with partial derivatives are present. How my will get transformed? So this will be a matrix transformation now with this Jacobian kind of partial derivatives multiplied with that original error matrix, which is a function of x. So this derivation one can make it. Okay. So this is simply, it is simply my. So it is like a basis transformation. So my is equal to T transpose mx is the original basis and then T. So here T is the error transformation matrix, and you see it is n-dimensional. So I do not care about the dimension, it goes on. Okay. So that means for Gaussian errors we can do anything now, right? So basis transformation from one coordinate system to another coordinate system, n-dimension, all correlated, everything we can do. Okay, we can deal with correlated errors, arbitrary dimensions, and parameter transformations. Okay, so this is, I know this is little higher dimension what I talked about, but this will help the advanced learners. Okay, so let me take one example to show this so that it is convincing. So if I measure two uncorrelated variables, for example, A plus sigma A, B plus sigma B, the error matrix can be written like this. Okay, and since I have told that it's uncorrelated, so your off diagonal correlation terms will be 0. So I calculate what is my M inverse. Now I am to estimate the two derived quantities x and y, which are A plus B and A minus B respectively. So now it is essentially equivalent to the basis transformation of the coordinate transformation, right? So now I write the transformation matrix, which is essentially the Jacobian matrix, right? Sigma x sigma A, and then sigma x sigma B, and similarly for y. Okay, and given the formula, so you calculate, you will find your T is 1, 1, 1 minus 1, and you put up this formula which I derived for you, My is equal to T transpose mxt. Once you are putting it and doing the recalculations, so you will find your sigma x square is equal to sigma y square is equal to sigma x square plus sigma b square. This is exactly equivalent to what I wanted, or what I was supposed to get from the error propagation formula. Namely, if x your x plus y and x minus y both should give you the same answer, and your rho is this. Okay. So now, as you can see, this this basis transformation, what I did using error transformation formula, so that is equivalent to in the generalized form what I obtained earlier. So little homework for again advanced learners. It will be difficult for general audience. So given the results of two straight line fields, calculate the uncertainties on the interaction. Meaning you have set up data points. Okay, and note the treatment of Gaussian errors via error matrix is an extremely powerful technique. Okay, so once you do in your programming, you will understand this is very important. So the homework I am giving you is, so you have set up data points, so they are crossing each other. Okay, and after fitting, you have a straight line fit for this one, straight line fit for this one also, right? So in the straight line fit, you have two parameters with uncertainties. Here also two parameters with uncertainties. So now in the interaction point, okay, you find out what will be the error. So this is a beautiful problem, and I have shown the solution also. It is a bit complicated, and if you do it, so you will enjoy all these error transformations. So the way I have written here, one set of data points will follow y is equal to alpha x plus c, another set will follow y is equal to beta x plus d. So now that the interaction point where they intersect, so you have to find what is the error on that. Okay, it is a beautiful problem. So it is complicated. So you try to do it and have a flavor. So is there any question on this? Because I am almost done with what I wanted to discuss, and next 10 minutes I will just go for least square fitting. Linear regression. Sorry. Any questions on this? Or we can come back at the end also. Okay, so it doesn't look like any quick questions. So then what I am doing is, so let me go. Let me go to my okay, so next 10 minutes I have a couple of slides to talk about method of least squares. Okay, so you can see my this presentation because this is another presentation. Yes?
Yes, sir.
Okay, perfect. So I am going to cover actually curve fitting, and I will stick myself to linear fitting or linear regression or the straight line fitting. Okay, so now let me develop the theory for that. Although it is discussed briefly, so this will give you a flavor how the fitting is done. So mostly we use some predefined functions like origin, xmgr, or any other function. Somebody talked about R language and Python yesterday, but more often actually these are standard developed softwares, and we do not care how the fitting is done, how to characterize the fitting, if it is a good fit or not. So let me develop the next 10-15 minutes. So we can go slow because there is no problem. Only thing is, I have not taken my breakfast. So in experiments, the functional relation between two or more variables describing a physical processes, which I write y is equal to a function of x1, x2 and xn, is investigated by measuring the value of y for various x, y, z. Okay, because this is the measurement you do. So it is then desired to find the parameters of a theoretical curve which best describe these points. So it is essentially you fit a theoretical formula with many parameters depending upon your formula, and you try to find out those parameters. So that is called your curve fitting. So for example, to determine the lifetime of a certain radioactive source, measurements of count rates which I showed you last time, N1, N2 and N at various times T1, T2 and Tn, that could be made, and the data fitted to the expression, Nt is equal to N0 exponential minus T by tau. So this radioactive formula we know, so this is fitted to find out the radioactivity at any given time. So since the count rate is subjected to statistical fluctuations, the values Ni will have some uncertainties, which is sigma I, and this is root over of Ni because these are counting experiments, and this will not lie on the smooth curve because this fluctuation will come up, right, in your measurements. So this brings up the concept of least squares. Now let us suppose the measurements at n points xi are made of the variable yi with an error sigma I. Okay, and I have n number of such measurements. So that is desired to fit a function which is f of x, and there are many parameters a1, a2, am. Okay, so these are unknown parameters, and my aim is to, after the fitting, I should actually have the estimation of these parameters and their corresponding errors. So the number of data points must be greater than the number of parameters. We know this, right? So number of data points I am going to fit should be always greater than the number of parameters in the theory. So otherwise it will be a problem. So you cannot solve the problem. So the method of least squares states that the best values of aj, these parameters, are those for which the sum, I define the sum s is equal to sum over I1 to n. yi is your measurement corresponding to xi minus that theoretical formula which you want to fit. So that value of xi using the parameter aj, so that functional value, divided by sigma I, the error on that xi measurement, is a minimum. That means the deviation of your measurement from the theoretical curve, okay, So that deviation weighted by your sigma I, which is the standard deviation or the error on that xi, should be minimum. That means your measurement should be as close to the theoretical formula as possible. And that is the whole procedure. My function should be the best function, best fitting to the data points. Okay. So this is the sum of the square deviations of the data points from the curve of xi weighted by the respective errors on yi. This is also called chi-square minimization because we have seen this kind of function. Strictly speaking, it is not quite correct as yi must be Gaussian distributed with mean fxi and aj and the variance sigma I square in order for S to be a true chi-square. However, as this is almost always the case for measurements in physics, this is a valid hypothesis for most of the time, and the least square method, however, is totally general and does not require the knowledge of parent distribution. So when I talked about fxiaj, I have not told you what kind of parent distribution is. Okay, so this belongs to a particular known probability distribution function or your first order polynomial, second order polynomial and third order polynomial I have not talked about. And your xi and yi are actually the measurements you have performed. Okay, and you are trying to see how close is your theoretical distribution is to your data points. So that is why a prior knowledge of the parent distribution is not necessary. We know this. So if the parent distribution is known, the method of maximum likelihood can also be used, right? Because when parent distribution is known, so you try to see through the maximum, the method of maximum likelihood, how close your data points will be to the parent distribution. So in case of Gaussian distributed errors, this yields identical results. We have seen this thing. Okay. So now let's go ahead. So the aim is to find out aj. We should solve the equation del s by del aj is equal to 0. So that is the maximization problem. So depending on the function fx, the above equation may or may not yield the analytic solution. Always it may not be easy to solve this problem. Okay. In general, numerical methods requiring a computer must be used to minimize s. So depending upon the complexity, so you may use s or you can solve analytically. Okay. Assuming we have the best values for aj, it is necessary to estimate the errors on the parameters. For this, we form the so-called covariance of the error matrix Vij, and Vij is defined in this way. So you have seen this earlier, this correlation error matrix. The second derivative is evaluated at the minimum. So for the second derivatives, for the inverse of the error matrix, okay. So the diagonal elements Vij can then be shown to be the variances for Ai, okay, while the off-diagonal elements of Vij represent the covariance terms between Ai and Aj. So I can write V now in terms of the elements. So the off-diagonal terms are your sigma 1 square, sigma 2 square and sigma 3 square, that is expected, and all off-diagonal terms will be your covariance terms of the cross terms 1 with 2 and all that. So now once I try to solve it, if I can take the simplest example, so you solve that one and you will get the answer for any s. But if I take the simplest example of linear regression, which is a straight line fitting, so I take y is equal to f of x, which is mx plus c, okay, and m and c are the parameters to be determined. So now this is my, so whatever I described as a part of the general theory, so now I am simplifying that for a known straight line. So now your s can be defined as sum over of yi minus mxi minus c divided by sigma I. So I take the partial derivatives with respect to m and c, set it to be 0, and to simplify the formula I redefine what is my a and what is b in terms of xi and sigma I square, so that my formula becomes easier. Okay. So with this redefining A, B, C and D. So this minimization problem now reduces to a simple arithmetic formula, okay, and the solution of which can be written in terms of A, B, C, D and E. So to estimate the errors on the parameters, the inverse error matrix can be written in this way, where this kind of complicated equations will come up. So see, when you do the fitting, all these things are going on in the programming part. You may not be knowing, okay. So finally I get sigma square m, sigma square c. So I wanted the errors on the value of m and c, which I got from the equation below 5, and then from the equations which I have written for sigma square m and sigma square c. So finally I have the parameters m and c and their corresponding errors. So this is the calculation you have to do for straight line fitting and no, and the covariance term also. Okay, so yeah, so that is what I wanted to discuss, and then looking into I think for a completeness I should talk about that, although I am extremely tired, I don't know why. Yeah, I think this can be the last slide. So to complete the process, now it is necessary to have an idea of the quality of the fit. So I did the fitting, I got from the linear regression what is my parameter m and c and corresponding errors, okay. So I know how to get it now, and can I quantify the quality of the fitting? So do the data in fact correspond to the function fx we have assumed? So if I ask this question, how good my fitting is, so this can be tested by means of chi-square. So this is just the value of s at the minimum, and I remind you that if the data corresponds to a function and the derivations are Gaussian, s should be expected to follow the chi-square distribution. So this formulation of s is quite general compared to the Gaussian case, where a chi-square distribution is expected with mean value equal to the degree of freedom d. So if there are n independent data points from which p parameters are extracted, the degree of freedom which was discussed in one of the classes earlier, so degree of freedom is equal to the data points, number of data points minus the number of parameters. So d is equal to n minus p, and for this problem p is equal to 2, because I have done a straight line fitting, it's 2 parameters. So your d is equal to if p is equal to 2, your d is equal to n minus 2. So if the linear fitting is good, s is expected to be close to d is equal to n minus 2. So I define a reduced chi-square, which is chi-square per number of degrees of freedom. So chi-square by d. Okay, this should be very close to 1 for a good fit. If it is much higher than 1, the fitting is not good, and you have to relook into the procedure or the function, or bring up another function which can do the better job. So chi-square per NDF should be as close as possible to 1. Don't try to do it artificially, but try to see. But sometimes there can be overfitting problem. Okay. So to test further, so that is something called p-test. Okay, the probability of chi-square greater than equal to s. So for this, what you have to do is, so you take the chi-square value obtained from the fitting and the degrees of freedom you know. So you look into the table given in some of the books of statistical data analysis. So you try to find out what is the probability of the chi-square to stay more than s. So if p chi-square greater than equal to s is greater than 5%, the fit is acceptable, and this will correspond to a particular degree of freedom. There is a table, so you can look into. So if you suspect your fitting or not in a good position to interpret if the fitting is good or no, so go for the p-test, probability test. So this p-test table is given in many of the books, so you can find out that table. It is just what is that called, You have your chi-square, you have your number of degrees of freedom, then there is a table of chi-square and number of degrees of freedom. You find what is the percentage. So that percentage will tell you if it is more than 5%, then the fitting is acceptable. Okay, I think this finishes my discussion on, yeah, so I don't need to discuss this. Yeah, so this essentially finishes my discussion on linear fitting, and for non-linear fitting, that is a procedure of linearization. For example, if it is exponential or log, so you can linearize that and then adopt to the same procedure, fitting procedure. But the point to note is, more often we use this fitting procedure as black box. Okay, and I insist the nuclear and particle physics in the audience that sometimes you should, after the fitting, you should look into your error matrix. So there is in root there is a command to look into error matrix after the fitting, and that will give you, if your off diagonal terms are non-zero, so the parameters are correlated, and parameter correlation should prompt you for different kind of interpretation of physics when you write your scientific paper. Yeah, so I think as per my plan, I am done with this. So thank you very much. If you have any quick questions, you can go ahead.
Thank you so much, sir, for this informative talk. Now I would like to request the audience, if anyone want to ask question from Sahu sir, they can turn on their mic and ask.
Sir, I have a question. Sir, where can I find an example for how the error propagate in a least square method?
Error propagating on least square method. You need one example. You see, as I showed you in the least square, the derivation, the formula. Okay. So the formula, whatever we got. So for example, sigma square m, the error on m when I calculated, although the calculation was a bit long and I had to rewrite in terms of a and b. So everywhere error propagation is done. So for example, in the error matrix, I showed towards the end in at the end of my calculation, I showed you in the error matrix that this uses error propagation formula, right? Did you recall in one of my slides after the error matrix? In that particular example, I also showed you that master formula for error propagation is valid. So here in the linear regression also, while finding out the error on M and C, so we use this coefficients A1, A2 and all that. So you will find that also uses the formula for error propagation. So error propagation is used everywhere because your data points are having errors. Unless that is propagated properly, you cannot get the parameter errors properly. And
Sir,
yeah.
Sir, I want to know not in the formula for A22 upon A1 in a matrix form. Error propagation in a matrix form itself.
Error propagation in the matrix form. I did it. I showed you some examples. Right. Yeah, in my earlier slide, I showed you. Let me take out my earlier. Error propagation in matrix form, I showed you here. Right, in this example, can you see now?
Yes, sir. Sir, can you suggest me a book for just for least square method?
Least square method is very standard. You can find any book. Go to Taylor and yeah, John Taylor or Roger Barlow, Statistics by Barlow or Error Analysis by John Taylor.
Okay, sir. Thank you, sir.
Yeah. So I used error propagation formula in the matrix form. Yeah.
Hello, sir.
Yeah.
Yes, sir, if we want to use the least square method in the higher order curves like parabola or anything else, then how we can define its efficiency for the higher order curves? I mean to say, will it be same efficient as we can fit it through a straight line, or
Yeah, both are, you see, linear regression and non-linear regression. These two are different. So for simplicity, because we have mixed audience, I showed the simplest straight line fitting and how the fitting parameters are extracted and the corresponding errors. But if you go for non-linear fittings, which are you are saying parabola and other things, so the fitting procedures are same, but the mathematics involved is a bit complicated. That is the reason I have not showed you. And you can have a look at any of the books I mentioned, like Taylor and Barlow. So how nonlinear fitting, nonlinear regression is done. Okay. So only your procedure will be different. The complications will be different. But as you might have noticed, if you are using any developed software like Root or anything, or your origin kind of software. So there already the program development is done, right? So you just choose your function or write your function and the program does the work. But at the background, how the work is done, what is the basic theory? So this linear regression should have given a little exposure how it is done. And if you go to linear to non-linear, there are some functions which can be linearized, right? If it is exponential, you take a logarithmic, so that becomes linear. But that is not the case always. So if you go to parabola or other kind of expressions, you may not be able to linearize it. So then your non-linear regression has to be used. And that procedure is discussed in any of the books. I have not discussed because first thing is time constraint. Second thing is a mixed audience. So if I give a big picture, many people will be lost. That is also another reason you have to find a intermediate path.
Okay, sir, I will go through the books.
Yeah, so just go through the books I mentioned. If there is any doubt, so you just drop one email as per my convenience. We can sit over a Zoom meeting and I can convince you how it is done. Okay.
Sir, this is the question from Arjun. He is
Yeah.
saying in the example where you are discussing about subtracting the background radiation. In such case, if we want to study the background radiation itself, like Bremsstrahlung radiation, how should we modify the method of observation that you are talking about in this example?
Method of observation. You see, what I talked about is you have signal plus background, and you have you remove the signal of the source. You have only background, and your detector is same. Okay, so you study the signal and background. Your detector has to be same because efficiency will come into picture. And once you have counted the numbers, you just apply the square root rule for the errors and use the formula your R based is equal to that total number divided by time and use the square root formula. That's it. It is very simple. And I have not talked about the detection techniques. Detection techniques are different, and the signal and background you should use the same detector because detector efficiency plays a role in the number of counts.
Hello, sir.
Yeah.
Sir, actually, I have asked the question from a different point of view. That is, while we are subtracting the background radiation, we are taking the background data for 3 minutes and the major data for longer time. So my question is that if we want to study that particular background radiation, like that we do in the Bremsstrahlung radiation, so then what kind of time measurement should we apply for that example?
Time measurement. Your question is on the time measurement.
Yes, sir. Actually, for how much time interval should we observe that?
Yeah, you see, it is user specific because as I told you, how much time I should do my experiment completely depends on me. Because the aim is to reduce statistical error, and statistical error in counting experiment that goes like square root. Okay, so depending on that and given your time in hand, so you take experiment, you take the measurements as per your wish. And usually what people do is background subtraction procedure, you take less time. You essentially devote less time for background estimation. But if you can estimate for longer time, that's better. It is user specific. There is no thumb rule that your signal extraction with background, so you observe for 1 week, and your background also you should observe for 1 week. There is no rule for that. It is completely dependent on you.
Okay,
Only aim is to reduce the statistical fluctuation. Okay, there is no rule.
yes, sir. Thank you.
Yeah, because you see another angle is, for example, if you ask me the question why LSC is taking data for a particular kind of collision for 2 days, you take for 20 days, okay, you will have better statistics. So then the answer is who pays for the energy expenses? For a day energy expenses is used to maintain the accelerator running. Right. So that is why you have to go in an optimized way. My expenses should not be very high. Expenses in terms of money, expenses in terms of manpower and time should not be huge, and expenses in terms of computing resources, because there are many things involved. The time is not independent time, right? So time is
Yes,
associated
sir.
with many other things, money, manpower, computing resources. So let's say I take additional data which is 5 times beyond my requirement. So then गाली मिलेगा फ्रेंच गवर्नमेंट से लेके इंडियन गवर्नमेंट तक, क्यों बर्बाद किया पैसा, राइट?
Yes, sir.
So you have to keep that angle also in mind. So that is why proper mathematical estimation is done. So if you look into, actually it is beyond the discussion here. So event statistics. So if I am looking into a particular kind of event, so with all given parameters like detector efficiency and all that, with luminosity of the machine, event rate and all that, I have to estimate minimum how many hours I should run my accelerator. So that estimation should go when you request for a beam time. Okay, it is not abrupt that we have a plan of running for 2 days versus 20 days. No, there is mathematical calculation to convince the funding agencies. I need to run my experiment for 10 days because of this. Do you think that getting money from funding agencies is easy? No. Okay, so that involves exact calculation of things and so on convince, because everything could be easy, but getting money is not easy. For research purpose, of course. Okay, I think I could convince you, right?
Yes, sir. Surely.
Okay, thank you.
So any other question? Yes. Sir, I think we have done with the question part. So on
So
the
I have a
behalf of,
question.
okay, yes.
Sir, why the reduced chi-square should be close to 1 for a good fit?
Yeah, reduced chi-square close to 1. So, if you just analyze that part, I told you that either chi-square or S, so which are actually both are in the Gaussian limit, both are same. You will find that your measurement should be very close to 1. Your measurement should be very close to your line, the fitting function. So if you see in terms of the standard deviation and the discussions I made, uh, your chi-square for NDF should be close to 1 for a better fitting. So by that actually your data points will be very close to your theoretical formula of the fitting. And if it is too high, so your fitting should be discarded. And before you discard your fitting, so I suggested you that to look into overfitting and all that, you should look at the p-value, that p-test, which I have not discussed. I guess Professor Majumdar discussed it earlier, but I had a plan to discuss, but I am extremely tired. Maybe early getting up and without taking breakfast, sitting for a long time. I am too tired. Otherwise, I would have spent another 10 minutes to discuss that. Maybe some next time.
Thank you, sir.
Okay, yeah.
Yeah, okay. I think Shubham, we should allow him to take some rest and breakfast.
Somewhere I'm feeling
You
tired.
can ask him later on also, yeah.
Yeah, maybe if there is any longer discussion necessary, drop me an email and I can be available in Zoom sometime. Okay, so we can have little longer discussion. But some way after getting up too early and then
Yeah, yeah,
breakfast
no,
ready.
absolutely, we understand.
Sorry.
So I think personally, I would also like to formally thank you. Raghunath, he has been guiding and supporting us since we first thought of organizing this workshop. And we always, I told on this inauguration day also that we always felt he is one of the members of the local organizing committee. So actually, he has been carrying out the dual role here. So as an expert also, as well as giving this valuable inputs in the workshop. So we are extremely thankful to you, Raghunath.
Yeah, you are welcome. So I enjoyed everything. So yeah, thank you, thank you.
Yeah, thank you very much, sir. Thank you very much for all what you are doing.
Okay, so see you sometime physically.
Yeah,
Either.
yeah,
Yes, sir.
sure.
Yeah.
Thank you, sir. Thank you so much. Thank you, sir.
Thanks, Yasser. Thanks.
Okay, have a good day.
Okay. Yeah, you too. Yeah.
So with that, we are coming to the end of our session. Let's meet the evening today at 3 p.m. Yeah, so please again, as per the request, kindly try to join 5 minutes before the actual scheduled time. Right. Thank you so much. Thanks, everyone.
Good afternoon, Professor Naik. Good afternoon. Yeah, I think your mic is muted. You are not audible actually. No. Yes.
Can you now hear me?
Yes. Now we can hear you.
Yes. Okay. Okay. Thank you.
Welcome, sir. Welcome. Thank you for joining. Yeah, Ankush, you can start.
Yes, sir. Okay. I don't see the option to share.
Uh,
It says that
just
only.
let me make
Yeah.
you the presenter. Just a minute. Ankush, you can start in the meantime.
Sure, sir. A very good afternoon to all of you. I, Ankush, welcome you all to the second talk of day 3 of short-term course. On the behalf of Department of Physics, NIT Jalandhar, I welcome Dr. Arun Kumar Nayak, and I feel a great pleasure in introducing him to all of you. Dr. Nayak is currently working as an associate professor at Institute of Physics, Bhubaneswar. Previously, he was serving as Reader F in the same institute. He has completed his Ph.D. from TIFR Mumbai. He has worked with various laboratories, including Laboratory for Instrumentation and Experimental Particle Physics, Lisbon, Portugal, Institute of Research into Fundamental Laws of Universe, France, DESY, Hamburg, Germany. He has been working actively with CMS collaboration for last 10 years and he has several cited papers. Professor has been honored with several awards and fellowships. He was awarded Ramanujan Fellowship in 2015, DESY Research Fellowship in 2014 and many more. Today, Dr. Nayak will be discussing some topic of statistics and will be very thankful to Professor for his knowledge. Now I request Professor to kindly enlighten us. Over to you, sir.
Thank you. Do you see the slide? I don't know what exactly I said because it doesn't show me my PDF file.
It's showing blank.
Okay.
Nothing is
Showing the PDF. Okay. Can you see it now?
yes.
Yes, sir. Yes. So you can make it full screen.
Yeah, that's what I'm trying to do, but it's not. Okay, now full screen mode. Okay, is it full screen now?
Mm, no, sir.
Yes, but probably it's good enough. I think we can get
Okay,
started.
because it's full screen in my screen, so I don't know. It's not.
Oh, okay, sir. It's large enough. We can continue.
Okay. Thank you. Okay, I would like to thank the organizers for inviting me to give this lectures. I think I have two lectures today. One is today, and another is tomorrow morning. And thank you very much for the nice introduction. Okay, so I think you already have quite a few lectures about uh, probabilities and point estimation, I guess, using um, statistical method and as well as the maximum likelihood techniques. So, what I am going to discuss today is regarding hypothesis tests and setting confidence intervals and limits. Um, okay, as you heard about me, I am mostly working in particle physics experiments. So, I am not sure the audience is from physics or from different backgrounds. So, So I will be mostly talking things which will be close to my areas because I do not have much expertise in other areas and applications in other branches of science. And here are some references, and again, these references are mostly related to the areas I am working in. So, but you may find also useful. Maybe the examples may not be uh, relevant for you. Okay, and I actually took most of these materials from this first
Sir, are
reference.
you in the first slide? I think slides are not changing.
Oh, okay. So I think that is
Yeah, no, it's
okay. So if I make full screen, I think it is not changing. Okay, I just have to keep it like this.
Could you please could you please blow up the whole screen so that we have a full screen view of the presentation?
Is this okay?
yes, it's fine.
Seems okay. Yeah.
Okay. Okay. Good.
Thank you.
So yeah. So and most of the figures and tables that are also taken from this reference. Okay, so let me start with what is called the statistical inference. So what we want to do here, or our goal is to make a statement about the compatibility of something that we observed in an experiment. Okay, so with some hypothesis, so we have say some hypothesis or some theory that we are testing with some experiment, and we want to make a statement about the compatibility of that hypothesis with the data that we observed in our experiments. Okay. So hypothesis is what you have probably already know. So it's basically say a hypothesis H which specifies some probability density f of x given H for a set of random variables x, where x could be outcome of some observation or data. So X could be say some univariate variable or some multivariate variables, continuous or could be discrete. And a sample space is the data space S, which consists of all possible values of X. If the hypothesis determines the probability density uniquely, such hypothesis is called a simple hypothesis. Or if it contains unspecified parameters, say like some parameters theta, and the hypothesis depends on that unknown theta, so such hypotheses are called composite hypothesis. So I guess I don't have to introduce likelihood. So anyway, the probability for X given the hypothesis H is called the likelihood of the hypothesis, or normally denoted as L of X given H. I guess you already had the likelihood, maximum likelihood estimation, so I can skip this. Let's go to what is called a test. So what we want to do is we want to test the validity of a hypothesis, and such task often involves making a comparison with an alternative hypothesis. Say we want to test a hypothesis called H0. Okay, some say we are expecting some signal, and in our theory, and we want to test whether the data is compatible with the only hypothesis, or it is something else. Okay, so we are testing the background only hypothesis against the data. Okay, sir. Yes. Yeah, please speak up. Can you hear me?
Yes, we can hear you. I think.
Okay.
Yeah, you can continue.
Okay. So a test of say H0 is defined by specifying some critical region, a critical region R, in the data space, so that the probability to observe the data in that region, assuming that H0 is correct, is less than some small value alpha. That is, if we write like this, the probability for X within this region R, given the hypothesis H0, is less than alpha. Such where this alpha is normally called the significance level of the test. Okay, and if X is observed in that critical region, then we can reject the H0. So like this. For example, if we want to test this H0, so we define a critical region, the region above this line. Okay, and if our observed one, the probability to find the observed one is in this region. Okay, so then we can reject this hypothesis. But this critical region is not unique. You can define it in infinite number of possible regions that can give the same significance level alpha. So to test the validity of this hypothesis H, we need to involve making an alternative hypothesis and compare it with that hypothesis. Okay, so the alternative hypothesis is say H1. Okay, so then you can define this critical region in such a way that the probability for H0 to be true is low, while the probability for H1 to be true is high. Okay, so that is how you can define such a critical region. Okay. So as I said, we have say two hypotheses H0 and H1, and we have this joint probability, two probability distributions. Okay, for probability of finding X given the hypothesis, and as I said, we can consider H0 as the background hypothesis, and H1 is say signal plus background hypothesis. Okay, suppose we want to select events of type H1 and reject events of type H0. So then we can apply codes on individual variables. So when we are doing some selections, some two type of events, some selections, so we apply some codes, right, on individual variables, or we can apply some codes on combination of some variables, say like topological codes. Okay, so how we can find an optimal way for this decision boundary? So the way is to construct a function t, okay, which is the function of the data that we observe, which we call it test statistic. Okay, so each hypothesis will then imply a PDF for the test statistics. Say we have this PDF, so g of t given h0 and g of t given h1, and then you can construct a decision boundary in by this cut, say t cut here. Okay, so the region above this cut is called the critical region. Okay, for this, and the complementary region is called the acceptance region. So it's basically combining the many variables in such a way that you get a 1D variable, 1D. So many ND problem reduces to kind of an 1D problem separating the two class of objects. Okay. Now, when we do this, and when you assume two hypotheses, so the significance level, as I said, is when we assume the hypothesis H0 is correct or true, so alpha gives the significance level, which is defined as the integration of this, say, probability from t cut up to infinity. So the region below this curve, above this t cut. But if we reject H0, if alpha is very small, then we can reject H0. Suppose alpha is below a certain threshold, then we reject the H0. In that case, if we reject H0 but H0 is true, we make an error there, right? Such error is normally called type 1 error, and the maximum probability for this to happen is normally the alpha. Okay, but there is an opposite one. Suppose we accept H0, but H0 is actually false. So sorry, this will be and some alternative H1 is true. So in that case, the error that we make is called type 2 error, and the probability for such error is given by beta, which is basically integrating from minus infinity up to t cut of this PDF t g of t given h1. So area under this second curve below t cut. Okay, so that's the beta, and 1 minus beta, that means the area under this curve above t cut, which will be 1 minus beta, would be called the power of the test to discriminate against the alternative hypothesis h1. So when you choose the critical region, the choice should be made in such a way that it maximizes the power while minimizing the alpha or the significance level against the alternative hypothesis. So here I give one example from my field. So suppose we have two set of particles, okay, say electrons and another particle called pion. Okay, when some particle passes through some material, they lose their energy. Okay, but different particles lose energy in different ways. So the energy loss for unit path length is different for different type of particles. Okay, suppose we have an experiment where there are both these kind of particles are there, and we want to select one type of this particle. Okay, and we use a test statistics, which is the energy loss per unit path length, so dE by dx. Okay, so that is our probability. So this is our test statistics, and then to know, so we can see the distribution of t, distribution of dE by dx, for electron and for pion, and then we can devise a threshold, okay, where we can maximize. Suppose we want to select electrons again and reject pions, so we can maximize so epsilon e 1 minus alpha and minimize say epsilon pi. So the threshold is be such that you can maximize one and you can minimize one. So like you apply a threshold to reject any class of objects. So let me skip this more detail. Now, what is the best way to choose a test statistics? Okay, or the optimal way, and how to choose the test critical region. So there is this so-called Neumann-Pearson lemma that states that the acceptance region giving the highest power and the highest signal purity for a given significance level in a test where of H0 against H1 is the region such that the ratio of their probabilities is above a given constant. Okay? So where this C constant is chosen to give a test of the desired size. So equivalently, we can choose the test statistics, which is this ratio itself. So the test statistics can be the ratio of this, which we call them as likelihood ratio. Okay, so there are various ways of constructing likelihood ratio. So usually, the explicit formula for PDFs are not known. So people use Monte Carlo simulation and then obtain the probability densities as multidimensional histograms. Okay, so then you can look at the histograms, choose the threshold accordingly, and so on. But if we have, say, m bins for each of the n components of x, and then the total number of bins, if you have a multidimensional problem and you have n bins for each component of x, and then you have n such components, then the total bins is basically m to the power n. So you need to have, say, sufficient number of data points to populate the histogram, okay, for this number of bins, and sometimes it becomes, say, difficult to populate such histograms. So you can have some compromise solution, assuming a certain, say, functional form for the test statistics with a fewer parameters, and you can determine such parameters using Monte Carlo simulation, and which gives the best separation between the signal and background. Okay. Alternatively, there are ways to estimate the probability densities using something better than histograms, and use the estimated PDFs to construct approximate likelihood ratio. So there are various ways. So I'm not going detail into how you should choose the test statistics. Of course, you can do also the currently the multivariate methods. Machine learning, we use machine learning to separate two classes of objects, and we construct the output of those such methods we can consider as our test statistics. Okay, now let me come to, so we said how to test one hypothesis against another, but suppose we are given only hypothesis H, okay, with the PDF P of X given H for a set of observables, and we do not have any alternative hypothesis. So, and we have some observation from the experiment, okay, X observed. So then what we can say about the validity of such hypothesis H in light of the data. So we have an hypothesis and we have observed some data. So what we can say about such hypothesis? So to test such compatibility, the hypothesis with the observed data, so without having specific reference to any alternative hypothesis, is normally called the goodness of fit test. Okay. So what we do here is, or how we do it. So we construct a test statistic whose value reflects some level of agreement between the observed measurements and the predictions given by the hypothesis H. Okay, so there is something called p-values. The p-values is basically the result of the goodness of fit test, which is expressed in terms of probability, assuming that H is true, of obtaining a result which is compatible or less than H than the one actually observed. Okay. Something like, you can assume, say, like, suppose no, if I can write it here. Seems not. Okay, so assume some distribution looks like this. Okay, and your mean is somewhere. That is your hypothesis, giving you a PDF, and you got observation which is somewhere here towards the tail. Okay, the probability from this point to positive infinity, that gives you kind of p-values. Okay, that is called the p-value. Note that this is not the probability for H to be true, since hypothesis is not treated as a random variable in frequentist statistics. Okay, but in Bayesian it might be possible. So in Bayesian you write this posterior probability, which is say p of x given H times this prior probability for H over integration of all such probabilities for all such hypotheses. Okay. So that might be possible, but we'll just concentrate on the frequentist method. Okay, now let's come to an example for calculating the p-values. I think that will explain better. Now let's see. We are tossing a coin. Okay, so that is our experiment. We are tossing a coin. So the probability to obtain, say, n heads in n such tosses is given by the binomial distribution that you know, right? And we want to test our observation against the hypothesis that the coin is fair. Fair means it should have same probability for having a head and tail, right? So the probability should be half. P should be half. So the hypothesis that P is half. Now we got some n observations, n heads out of n tosses. Okay. Now given that data, so we want to test if that coin was fair. So let's take the test statistic as the number of heads that we observe. Okay, number of heads. Now suppose we tossed coin 20 times and we got, say, 17 heads. Okay, so what is the value of the p-values? What is the p-values? Okay, in this experiment. Now the p-value says the probability of obtaining a result with the same level of discrepancy with the hypothesis or higher. Now what is this? So suppose we got 17 heads. Now we can look at the data space in that the region of this distribution. Okay, which are the ones which will have equal or lesser compatibility with H than 17. Okay, so that is with respect to 17. So the ones that will have lesser compatibility with H is the ones on both sides of the tail, right? 17, 18, 19, 20, and the other side 0, 1, 2, 3. Okay, so if we get heads out of 20, if we get out of 20 dozens, if we get this kind of numbers, okay, this kind of heads, okay, that will have lesser compatibility, lesser or equal or lesser compatibility than 17. So then what is the total probability? So the probability for finding these numbers, okay, out of 20 tosses will be, so you have all possible probabilities, okay, and out of that, if you do that, you will get a probability of this. Okay, so you will have to basically integrate the binomial distribution for regions above 17 and below 3 and divide by the total area, and that will give you this number. So the p-value is very small. Now let's come to significance of how do we calculate the significance of an observed signal. Suppose we did some experiment and we got some results. Okay, so if we have think that we have some signal, what is the significance of such signal? So let's consider a counting experiment. Okay, we don't have any distribution, we just have n number of events we have observed. Okay, and we expect from the backgrounds, say nb number of events, suppose, and we may observe some signal ns. So the total number of events n will be ns plus nb, and that the n is distributed normally according to the Poisson distribution. Okay, so which is given by this. Now, where S and B are your mean number of signal events and mean number of background events. Now, suppose we observed n observed events from the experiment. Okay. Now, can we make an inference about S or calculate the significance of S? So, if we find S is 0, then we can reject the signal hypothesis, or if we find S is non-zero, then we have to quantify our degree of confidence in the discovery. That means how many significance the signal is. Okay. So in both cases, what we are doing is we are comparing with the relevant alternative hypothesis. That is comparing with the background only hypothesis. Okay. Now, to compare background only hypothesis, we have to calculate the probability to get, say, n observed events or n observed or more events from the background alone. Suppose we don't have background only hypothesis, means we don't have any signal. So if we don't have any signal, what is the probability that we will get n observed or more events? Okay. So that is this probability for n greater than or equal to n observed. It's basically you can sum all the values from n observed to infinity for this Poisson distribution. Okay, with s equal to 0. Okay, so that is you can do reverse, because sum from 0 to infinity should give you 1. So that means you can write this as 1 minus 0 to n observed minus 1, sum of this one, right? Because this PDF is normalized, and this one is the binomial distribution. This one is given by b to the n by n factorial e to the minus b. So this is your value. Now suppose we expect b, we estimated b from Monte Carlo simulation or somewhere. So we estimated that the background should be 0.5. Okay, our mean background should be 0.5. And we observed, say, 5 events. Then what is the p value? So the p value here is n, probability for n greater than 5 giving b is 0.5. Okay, and assuming that this is background only hypothesis, so s is 0. And such probability p value, if you do this calculation, okay, then you will get 1.7 times 10 to the minus 4. Remember that this is not the probability for s to be 0. Okay, rather is a probability of obtaining n observed events assuming s is 0. Okay, the opposite. So note that also we have not considered any systematic uncertainty in V. So it has to be, if you consider systematic uncertainty, it has to be incorporated accordingly. Okay, now given the p values, you can also convert back to signal significance. Okay, so the significance Z is normally defined as the number of standard deviations that a Gaussian variable would fluctuate in one direction to give the same p value. So that is, if you have a Gaussian distribution like this, okay, and the significance Z is defined such a way that if you integrate this Gaussian distribution from Z to infinity, you should get the same p value. Okay, so if you do that, so the p equal to g to infinity of this Gaussian distribution. So that you can write, if you write as 1 minus phi of z, phi is the cumulative distribution of g, that is from minus infinity up to z. So if you integrate this minus infinity up to z, that is phi of g, and then g will be quantile of 1 minus p. So phi inverse is the quantile of the standard Gaussian. Okay. So if you do this, you will get g to be 3.6. So this is still not high. So if you get for 5 sigma discovery, the g z should be high, and that corresponds to a p value which is order of 10 to the minus 7 actually. So if you get a p value 10 to the minus 7, then you should say that we have some excess which is more than 5 sigma, or we have some signal which is more than 5 sigma, which is typically the threshold that we claim a discovery for something. Okay. Now I think I'll switch to the another slightly different topic, interval estimation. If you have any questions, please ask me in this, the things that I discussed. Otherwise, I can move on. Okay, it seems not. So let me move to interval estimation. So you have already had, I think, the lectures on point estimation, estimating some value of the parameters using maximum likelihood methods and using I can hear you.
Yeah, I don't know what happened. Let me make it.
Okay, we can restart.
Yeah, please see, and now I hope you will be able to share.
Okay. Can you see my slides?
Yes, yes.
Okay. Should we wait for some time?
Maybe 2-3 minutes. Can we wait?
Okay. Okay. Because yeah, people may not be able to join immediately.
Arvind sir, kindly restart the recording.
I think we can start actually.
Okay.
Okay.
Okay. Okay. So what I was saying is that yeah. So you had lectures about parameter estimation using maximum likelihood fit or least square method. So when you do parameter estimation, you also probably have learned how to calculate their uncertainties, right? So so whenever we do some estimation of parameters, so it is necessary that we report also an interval reflecting its statistical uncertainty. Okay, so you have calculated the statistical uncertainty in I guess in case of maximum likelihood fit and least square method. Okay, so the interval, okay, should have some desirable properties. Okay, that means it should be able to communicate objectively the result of the experiment. It should have a given probability of containing the true parameter. Okay. and the, it should provide also information needed to draw conclusions about the parameter, possibly incorporating stated prior beliefs. Like, in some experiment you cannot have a signal which is negative, for example, right? So such beliefs, which, like before starting experiment, that you cannot say that I can have a signal which will be negative. Okay, so such beliefs should be able to be incorporated while drawing some conclusions out of this concept. Okay, in most cases we use this plus minus sigma, right, for this estimate theta cap, and this is the estimated standard deviation of the estimator. Okay. However, in some cases this is not adequate. Okay, just quoting the plus minus sigma, 1 sigma. For example, if you are estimating near a physical boundary, like say close to 0. Okay. For example, an observed event its rate is consistent with say 0. Okay. In that case, how will you quote the uncertainty or interval? Okay. Now, first let's discuss the frequentist confidence intervals. The first rigorous and general treatment of these confidence intervals under this frequentist approach was first developed by Neumann. So, suppose you have a theta hat, the estimator for parameter theta. So you have had maximum likelihood estimators, for example. So, and we observed an estimate of theta observed. Okay, theta hat observed. So that is our estimate value of theta hat from the data. Now, we also need to know the PDF of this estimator for all possible values of theta. Okay, so such PDF we can write like G of theta hat given theta. And now you can find, so G theta is distributed like this in this set. So this is suppose the PDF. Now you find the upper and lower tail probabilities. So you define these two regions. Okay, region above u alpha and region below nu beta, so that the probabilities alpha and beta are given as following. So the probability alpha is the probability for finding theta hat above u theta or u alpha theta. So which you can write like integration from u alpha to infinity g theta. And similarly, the probability beta is the probability for obtaining theta hat less than nu beta. Okay, this probability, and that you can write like integrating minus infinity to nu beta. This one. Okay. Now we want to know, given alpha and beta, given these probabilities, how we can find u and v. Okay. Now, the region between this u and v. So this region between these curves, in the space theta and theta hat, you will have a curve for u alpha and curve for u beta. As theta varies, your theta hat will also vary, and for each theta. So here the probability is for one value of theta. Okay, this is a probability distribution for theta cap for a given value of theta. Now, when your theta value varies, the two parameter varies, this distribution will also change, and accordingly these values will also change. So in this 2D space, you will see the u alpha and u beta, which are the function of theta, will have these two curves. Okay, and this region between these two curves is called the confidence belt, and the points where observed estimate. So suppose for theta hat we did one experiment and we observed theta observed. Okay, so from one experiment we got theta observed. Now we want to estimate, we want to give the interval of for this theta observed. Okay, the confidence interval for the theta observed. So the values where this theta observed line, okay, intersects these two curves, nu alpha and nu beta. So these values A and B is called the confidence interval. The confidence interval is the interval for true parameter theta, not the estimate. Okay. So this is thing that you need to understand. So the confidence interval, when we give that interval is for the true value of the parameter. Okay. So this A and B is for this true value of this parameter theta, and in such a way that the probability for this interval to contain the true parameter theta is the probability 1 minus alpha minus beta. So that is the probability for containing this true parameter theta. Okay. So what we want to find is what is this value of A and B given the probability. Suppose we want to say 95% confidence interval. Then what is the value of A and B that contains 95% times the true value of the parameter theta. Okay. Okay. So how do we get this? So we can determine the inverse functions. So we can write A as u inverse theta hat, B as u inverse theta hat, right? And then our probability definition, these definitions can be modified like this. So alpha will be probability for A, which is a function of theta, is greater than equal to theta, and beta, which is probability for having probability for B, which is again function of theta, is less than equal to theta, and theta being within A and B, that probability is 1 minus alpha minus beta. Okay. And when alpha and beta are same, say like gamma by 2, such confidence intervals are called central confidence interval. And if we have with the probability 1 minus gamma, so alpha is gamma by 2, beta is gamma by 2, so the total probability will be 1 minus gamma. And if we have just one-sided, not both-sided confidence interval, such confidence intervals are called limits. So you give either upper limits or lower limits on a parameter, that this parameter is above certain value with this confidence level or below certain value with this confidence level. Okay, such things are called limits. So here in this case, A represents a lower limit on the parameter theta with probability 1 minus alpha, and similarly B represents an upper limit on parameter theta with probability 1 minus beta. Okay. Okay, so now how do we get this A and B? So by construction, A is that hypothetical value of the true parameter theta for which a fraction alpha of the repeated estimates would be higher than the observed value of theta. So if we consider A is the true parameter, okay, then we will find the distribution of theta hat like this, assuming A is the true parameter. Then if we observe, say for the theta hat, we got a observed value from an experiment, theta observed, then the probability alpha will be the probability under this and the area under this curve above this theta observed. Okay, so that you can write like alpha, which is from theta observed to infinity, g of theta hat given A. A is assuming A is the true parameter. Okay, so from here one can, so this you can write again like 1 minus integration 0 to or minus infinity to theta observed of g theta So that will be integrating from here up to this. Okay. So 1 minus this, and that this integration is nothing but your cumulative distribution of this PDF. So one can invert that cumulative distribution to get the value of A. Similarly, for beta or B is the hypothetical parameter, hypothetical value of the two parameter for which beta of repeated experiments would be higher than the value that we observe. So that means if we assume B is the two parameter, then we will have another distribution for theta hat, and suppose we observed our observation value is theta observed, then the fraction here gives it the beta. Okay, so that you can write again like this: beta is of integrating this distribution g theta at from minus infinity to theta observed, and this is your cumulative distribution for this PDF, and then you can invert it to get the value of B. Okay, and sometimes you may have to solve it numerically if you don't have a known cumulative distribution function. Okay, now we already discussed the p-value earlier, right? So there is a relation between the confidence interval and the p-value. What is that? We already said we did exactly similar thing for the p-value. So in case of p-value, what we did that, suppose assuming a hypothesis, okay, if we got some observed value, what is the probability that we will observe this some events which is above the one that is actually observed. So in that case, A was fixed, the hypothesis was fixed, and we calculated alpha. So alpha was the random variable that we calculated, which was our p-value. And in that case, the hypothesis A was given. In case of confidence interval, what is given is alpha. So we know at what confidence level you want to compute. So if we want to compute say at 95% confidence interval, alpha is 5%. Right. So in that case, alpha is given, and we want to calculate H, the random variable, which is estimated in light data. Can someone please mute? Okay, thank you. Okay, so I hope this is clear that what is the relation between interval and p-value. So in one case, A is known, A is given, or the hypothesis A is given, and we are computing alpha, the p-value. In another case, the probability is known, okay, and we want to know what is that value which gives that probability, okay, or the interval that gives this probability. Okay, so interpretation, you already give errors, right? You quote errors. So the intervals are normally quoted as errors. So the interval is a random variable, okay, where the theta, true theta, is constant, which is not known to us. But the interval, what we compute, assuming that the true theta, this is the probability to for this interval to contain the true theta. Okay, so suppose we have this 95% confidence interval. That means this interval contains the true theta in 95% cases. Okay. Typically, we report this interval as say like errors, like theta hat plus t minus c if they are asymmetric, okay, not central confidence interval. So we write like this, where c is theta hat minus a and d is b minus theta hat. As I said already, so the interval is constructed according to this above prescription in a large um, um, sorry. So how do you interpret this interval A and B? The interval A and B, it means that if you construct such intervals according to this prescription in a large number of similar experiments with the same sample size per experiment, then the interval would include the true value of the theta in 1 minus alpha minus beta number of cases, okay, or fraction of cases. So if you say 95% confidence interval, that means the true value of theta will be contained 95% cases within this interval. But remember that we don't know what is the true value of theta. Okay. So what we know is only the observed value of theta, and we know what is the estimator, okay, the PDF of the estimator. Okay. Now let's see how do we calculate the confidence interval for a Gaussian estimator. Okay. So if our estimator is distributed according to Gaussian, okay, so we can write the cumulative distribution function for this estimator, which like we can write like minus infinity to theta. Okay, so minus infinity to theta, and then this Gaussian function, right? So this kind of case is commonly occurring. As you know that in many cases you will get the estimator to be Gaussian because according to central limit theorem, the sum of random variables becomes Gaussian. Okay, so if your estimator is kind of a sum of many random variables, then the estimator would PDA for the estimator would be Gaussian. Okay, and now suppose we know the variance or sigma of the theta hat, okay, is known, and we observe some estimate theta hat observed, okay. Then we can calculate the interval A and B, which can be given by solving this set of equations. So alpha will be 1 minus g of theta observed, given assuming A is your true value of the parameter, so which you can write like 1 minus phi, and this, but phi is the CDF of the standard Gaussian. Similarly, beta is the CDF of theta observed, CDF for theta observed, given sorry, I think this should be B. I made mistake, so I can correct this later. So given assuming that B is the true parameter, so that you can write like this, and then you can invert them and find what is the value of A and here phi inverse is the quantile of the standard Gaussian. So here you can see, for example, the central and one-sided confidence intervals for the standard Gaussian. So here for the central interval, so if both side probability is gamma by 2, and for the one-sided confidence interval, the one side is, say you can take gamma or something. Okay. Okay. Now, typically when we quote error, we quote error with respect to 68 point interval with respect to for 68.3% confidence interval. Okay. So that is, we say 1 sigma. 1 sigma corresponds to typically this, which is, then we can take alpha equal to beta equal to gamma by 2, and for 1 sigma, phi inverse 1 minus gamma by 2 is 1. It's 1 sigma error bar, and the measurement typically is reported like theta observed plus minus sigma theta. Okay. In some cases, you may not know what is the sigma or the true standard deviation for this theta hat. In that case, one can estimate it So they estimate this from data, and we can use the estimated value of this sigma, which should be close to the true value for a large enough data sample. Okay, so here you can see the values of this phi inverse for different probabilities. Okay, so for 68.3 confidence interval, phi inverse should be 1. For 95.954, okay, typically we say 95% confidence interval, it is 2, and 99% confidence interval, it is 3, and so on. Okay, so and similarly, this is for the central confidence intervals, and this is for the one-sided confidence intervals. Okay, and similarly, you can also see the other way around, the values of the quantile for different confidence levels. Like if we want to set the interval for 90% confidence level, 95% confidence level, or 99% confidence level, what should the value of phi inverse in this equation? Okay, so depending on what probabilities you want, what is the value of 1 minus alpha or 1 minus beta, depending on that, you can set the value of phi inverse here to get the corresponding confidence level. Or if you know the confidence level, if you know the if you desired confidence level, you set accordingly, and if you desired say like phi inverse values, then you will get accordingly this confidence level. Okay. Now we discussed about the Gaussian parameter. We can further discuss about the getting the confidence interval for the Poisson parameter. Can I take some more time, or how much time can I take? Okay, I think I have a few more slides, so I can cover this. So suppose we have an outcome of the experiment which is a Poisson variable n. Okay, so it is discrete. So then the Poisson PDF looks like this, where nu is your mean number, and in this case, suppose you want to get a confidence interval AB for a given observed value of nu. So that we can obtain by again using the same kind of relations. So alpha is the probability for observing nu greater than nu observed, given A is the mean number, or A is the mean number, and beta is the probability for observing nu less than nu observed, given B is the mean number, right? So from there you can invert, and then you can calculate further. So alpha will be like you do the sum for this n from n equal to n observed to infinity. So that you can write in opposite way, like 1 minus n equal to 0 to n observed minus 1, because from 0 to infinity the total should be 1. And similarly for the beta also you can write, and then there is a relation between Poisson distribution and the chi-square distribution. So if you sum over this Poisson distribution from 0 to n observed, this one is related to the chi-square distribution like this, with number of degrees of freedom as twice times n observed plus 1, and here that will result in 1 minus CDF of the chi-square distribution. Capital F is the cumulative distribution function for the chi-square distribution with this number of degrees of freedom. Okay, and then from there one can obtain A and B, the intervals, by inverting the chi-square CDF of the chi-square distribution, or it's called quantile of the chi-square distribution. Okay, so when you construct this interval A and B, so this will contain this much, contain the true value of the parameter, or this much probabilities. That is, probability for finding true value of the nu if greater than A will be 1 minus alpha. Probability of having true value of nu less than equal to beta, B is 1 minus beta, and for probability for having the true value of the nu between A and B It's 1 minus alpha minus beta. So here this table provides you all the numbers corresponding to a given probabilities. Okay, suppose we take alpha to be 0.1. Okay, so take this one sided something like this. So suppose we consider alpha here. So this is not Poisson, but this is Gaussian. But I'm just showing you imagine the equivalent of this for the Poisson. So from this threshold above this, suppose we consider this 0.1, 0.05, 0.01. So this corresponds to like this is the lower limit, this is the upper limit. So for that, and for a given value of the observed number of events, what is the lower limit A and B that you will get? This table gives you, so one can use these tables, and in fact I am going to use it in the future slide. Okay. Now let's see. Suppose n observed is 0. So we did some experiment and we got 0 events. So in that case, what happens? In this equation you can see that we cannot calculate L alpha because you cannot compute this sum. So what we will get is the upper limit beta. Okay, so the beta will be from n0 equal to 0, this, which is basically ether minus b, and from that you can say b is minus log beta. And for 95% confidence level, that means beta is 5%. Okay, so 1 minus beta is 95%. So minus log this is around 3. Okay. So that means if the mean was 3, the probability to observe 0 events would be about 5%. Okay. So that was about the Poisson variable. Now one can also obtain the confidence intervals from the likelihood function or the chi-square distribution. If some estimator is, say we have a maximum likelihood estimator, in the large sample limit the PDF becomes Gaussian. So you have, I think you have gone for this. Okay. So in that case, the likelihood function itself also becomes Gaussian. So you can write the likelihood function for theta as, I think it should be theta hat. So L max exponential of this Gaussian distribution. Okay, L max times this exponential Gaussian function. Then you probably already have used this RCF bound to compute the variance of the ML estimators, right? So in that case, you know that the log L value varies if you vary by plus minus n standard deviations with respect to the maximized value of the theta. Okay. Then this varies by n square by 2. So you can the log, so this relation, if theta varies by plus minus n standard deviations, then the likelihood function varies by decreases by n square by 2. Okay. So for one standard deviation it will be like 1 by 2. So L max, log L max decreases by 1 by 2. So you can see like this. So in this case, so this is an example for an exponential distribution which mean 5 measurements. So this, if when you plot log of L as function of tau, so this is the maximum value, so maximum like the value of the maximum value of this estimator. So where you get the estimate, your estimate, and as you vary tau, this log likelihood decreases, and where it becomes half, this gives you the one standard deviation, right? Okay. Similarly, if the estimator is, for example, unit square, like chi-square, so distribution is chi-square. In that case, the chi-square function here is like chi-square mean plus minus plus n square. So the value at which the chi-square increases by n square gives you corresponding n standard deviations, right? So for one standard deviation, the chi-square should increase by 1 with respect to its minimum. Okay, so I already discussed this. I can skip the multi-parameter case, I guess. So it's not what I is the upper limits on this Poisson parameter. Suppose with the background. So what we discussed earlier is that we did not discuss, we computed the limits in this case, intervals on the Poisson parameter, but we did not discuss about the background. Now let's say if we have backgrounds, okay. So now the total n, observed number of events n, will be a Poisson distribution where n is s plus b. Okay, so we can write f for n is s plus b for n by n factorial times minus s plus b. Right. Now suppose then we can define our ML estimator for S for signal, which is S hat is n minus b. Now we can find what is the confidence interval for this S hat given a observed number of events, n observed. Suppose we observed something, then what is the confidence interval for S? Now we can write like the same thing. So alpha is the probability for obtaining S hat greater than S observed. Even this in this place of A, I just write S low because that is corresponding to this S. Okay, the lower limit for S. And similarly for beta, we can write S is less than S observed given S of, assuming S of is the true parameter, true value of the S, and here assuming S low is the true value of S. So that we can write like this, summing about the Poisson distribution. Okay, so that will result. So that will result in S low to be again quantile of the chi-square distribution, okay, and minus b. So here you notice that with respect to the previous case, we obtained here a this minus b. Okay. Similarly, S of is minus b. So if you had no b, it would coincide with the previous case. Okay. Now let's take an example. Suppose we have background 4.5 and we have observed number 5. So we had 4.5 expected background and we have observed 5 events. So what is the upper limit on S at 95% confidence level? So we can calculate this from here. So we can say use S of one-sided confidence interval, okay, and we get that the upper limit on S is 6.0. So this picture using these numbers. So this picture here gives for each background values, if we have a corresponding observed number of events, then what is the upper limit on S? And you can see is that the upper limit for each background goes like this. Okay. So here you can see one thing, that suppose we have say 5 background events and expected background events, and we observe say two events. We expect 5 background and we observe 2. Then you can see that it goes negative. Okay, the upper limit on S goes negative. But we know that before starting the experiment, that S cannot be negative, right? It can be 0 or higher. So we cannot have negative. So we cannot give a limit, negative limit on an on a value or which after performing an expensive experiment, right? So we have to do something. So this is what I was talking about. So suppose say b equal to 3.5 and we observed say 0 events. Okay, we expected 3.5, but we did perform an experiment and we got 0 events. So for 95% confidence level, the upper limit if you calculate on S, you will get minus 0.5. But we already know that S is greater than 0 before we started the experiment. So what does the meaning of this negative upper limit expensive experiment? So for physics people, it doesn't make sense. Okay, but if you look at it, or if you ask statisticians, they will say it is not wrong. It simply means that this interval was designed to cover the true value in a certain fraction of repeated experiments. So in this case, we consider 95%. So this interval was designed to contain the true value of the parameter for 95% experiments. But we have encountered one of those experiments where this interval simply doesn't contain the true value. That is the case. But as we physicists, we would like to give the result of an experiment which also incorporates our previous knowledge of the true parameter. Okay, because for us the signal cannot be negative, so we need to incorporate that information somehow into our interpretation of the result. Okay, so how we can do that? So this can be done using Bayesian approach to the limits. Okay, so in Bayesian statistics, it starts with a prior PDF, phi of theta, which gives you the degree of belief on the theta before performing the experiment. So for example, in our case, that theta is for example positive. Say if we consider a mass of a particle, the mass of a particle cannot be a negative quantity. For example, if we want to measure the mass of electron using some experiment, the mass of electron cannot be negative quantity, right? So such belief we can incorporate, such belief we can use as a prior. Okay, and Bayes theorem gives us how the beliefs can be updated in the light of data. Okay. So posterior probability for obtaining theta given the data is the likelihood of obtaining the data given the parameter theta and times the prior probability theta over the integration or sum of all such probabilities, all such likelihoods. And one can use this posterior probability to determine the confidence interval instead of the probability densities. So this posterior probability we can use. So here now the redefine this alpha and beta probabilities in terms of the posterior probability, incorporating our prior beliefs. So the advantage is that it can incorporate our prior knowledge. For example, if something is positive, then we can set pi theta to be 0 for theta less than 0. Okay, that makes the posterior density posterior PDF to be 0 for theta less than 0. So then the upper limit will be simply, say, if we write 1 minus beta times minus into this p of theta x d theta, so that will make
video I am showing which you can watch on board.
Sorry, was there any question?
No, I think Sampan has unmuted actually.
Okay, thanks. So this now you can write as from here, if you integrate this from minus infinity to theta up, okay, so that will make this integration, and in this case you can say that when theta is less than 0, so if we use this prior where pi theta is 0 for theta less than 0 and phi theta is 1 for theta greater than 0. So this value, this quantity will become 0 for theta less than 0. So we will be obtaining a limit which will be positive. Okay. And okay, so there are many choices for the prior, so I am not going into detail onto those things. But okay, taking a flat prior, so here I am taking for example a flat prior for theta greater than 0. So this is sort of okay if the likelihood function dies off for a large value of theta. Okay, but of course this doesn't really reflect your reasonable degree of belief. Like you cannot have, suppose you are measuring say mass of electron, the mass of electron is positive, but it doesn't have the same probability for say 1 MeV and 1000 MeV. Okay. Okay. Now, if we incorporate this, okay, Bayesian limits while computing the Bayesian method while computing the upper limits on the Poisson parameter. So in this case, we can come back to this, and then we can get an posterior PDF. So we'll define the likelihood, okay, which is this Poisson probabilities. Then the posterior PDF will incorporate our belief for the prior here. Okay. Now, if we obtain again the upper limit at a certain confidence level, 1 minus beta, that will given by 1 minus beta to be this derivation, and then which you can write again like this. So you can see that on the below one integrates over all the possible probabilities, and then so this way the upper one goes from 0 to s of, otherwise for below 0 this pi is 0, and actually these integrals are related to incomplete gamma functions. So and one can use those gamma functions and then solve for this, and when you solve for this you will end up with again chi-square distribution. So you will get S of H inverse of this chi-square quantile of this chi-square distribution with this number of degrees of freedom, and here this value P corresponds to this one here. Okay, you will get this kind of expression. Now see that suppose B is 0, okay, which is our special case which we obtained earlier also. If B is 0, then you can see that this part becomes 0. Okay, so the P becomes basically 1, and you will end up with actually same numeric value as we obtained in the frequentist case. So for B equal to 0, we will get same result as the frequentist case. So this is just a coincidence, okay, that we are getting the same values. So here you can see the limits obtained incorporating this the flat prior. So here you see the distributions for different values of B and different observed values, observed number of events. What is the upper limit on the signal? So you can see that when so number of events is observed number of events is 0, the upper limit on signal does not depend on B at all. You can see this line, the lower line. Okay, this is more, it is flat, so it is completely independent of B. And for all values of B, you get a positive upper limit on the signal. So only where it matches exactly with this frequentist method is when B is 0. So this initial points. So that point you can compare between this plot and this plot, they are same. Okay. But here as you saw that you are going negative, but here all these limits are positive. Okay, so I think that brings to the end. So that's what I think I could cover in this lecture. Of course, there are a lot more things, advanced things to understand, and the ones that is typically used in the experiments and all these tools. A lot of things, of course, to know in this case. So what I discussed is mostly very basic things, and yeah, that's it from my side. So if you have questions, I'll be happy to discuss.
Thank you so much, sir, for taking pain to discuss all the basics. And with your permission, we can open the talk for questions.
Yes, yeah.
Yes, in audience, if anyone wants to ask anything.
Yeah, I think it was fully understood or it was nothing understood. So, okay.
So if there are no questions, then come let us thank the speaker for.
May I ask
yes,
whether it was even understood? I mean, I don't know at what level I discussed. Was it okay for
No,
the audience?
sir, it was really nice, and I myself was listening to it and got many insights.
Okay.
I believe audience were also attentive.
Okay, thank you then.
Okay, then. Yes, sir.
Thank you, Professor Arun, for taking out time. We know actually you have lectures in some other conference also as well, right? Probably
Yeah,
tomorrow.
I have a lecture. Yes, I mean talk, not lecture, but yeah, another conference presentation.
So tomorrow in the morning we will have this second talk at 10 a.m. right?
Yes, yes. So that will be on Monte Carlo simulation.
Monte Carlo methods, yes. Okay, so thank you, sir. Thank you for joining. And yeah, so for all the participants, tomorrow morning we will have talk a little earlier at 10 a.m.
Yeah, sorry, I had to reschedule because I have early afternoon. I have talk, so I didn't want to extend.
Yeah, that's fine. So
late.
no problem. Thank you. Thank you very much.
Okay, thank you very much. Thank you. Bye. See you tomorrow.
Thanks a lot. Bye.
Thank you, everyone.
So tomorrow is going to be only a single talk tomorrow morning, right? It's going to get started as told to us by Dr. Arvind that it's going to get started at 10, right? So please try to get connected by 9:55 a.m. so that we can get the timely start of that presentation. Yeah. Thank you very much. Thanks all.
Thank you, sir. Thank you.